In Module 3, we're going to discuss algorithm. Module 3 is divided into 3 parts: algorithm, growth of function, and complexity of algorithm. In this video lecture, we're going to focus on properties of algorithm and discuss some algorithm for sorting. There are many general classes of problems that arise in discrete mathematics. For instance, given a sequence of integers, we could find the largest one. Given a set, we could list all its subset. Given a set of integers, we could put them in increasing order. Given a network, we can find the shortest path between two vertices. So when presented such a problem, the first thing is to construct a model that translates the problem into a mathematical context. Discrete structures used in such models include sets, sequences, and functions, and such structures as permutation, relations, graph, trees, network, and finite state machines. Setting up the appropriate mathematical model is only part of the solution. To complete the solution, a method is needed that will solve the general problem using the model. Ideally, what is required is a procedure that follows a sequence of steps that leads to the desired result. Such a sequence of steps is called algorithm. The term algorithm is a corruption of the name Al-Khwarizmi, a mathematician of the 9th century, whose book on Hindu numerals is the basis of modern decimal notation. Originally, the word algorithm was used for the rules for performing arithmetic operation using decimal notation. Algorithm evolved into the word algorithm by the 18th century. With the growing interest in the computing machine, the concept of an algorithm was given a more general meaning. So to include all definite procedures for solving problems, not just the procedures for performing arithmetic. So let's have this example. Describe an algorithm for finding the maximum value in a finite sequence of integers. So in these slides, it discusses the following steps to determine the maximum value on a given integer. Okay, so algorithm could be represented by English, okay, or other means. And also, when we create an algorithm, it should be intended for all kind or for the same type of problem. Okay, so for example, so the maximum value, where can we implement it? So for example, in finding the highest score in an exam, or determining the someone from sports that has a good stat. So in basketball, in golf, in tennis, okay, etc. So that's why we are creating an algorithm, so that we could implement it in different ways, to solve problems. Okay. So an algorithm can be described using a computer language. However, when it is done, only those instructions permitted in the language can be used. This often leads to a description of the algorithm that is complicated and difficult to understand. Furthermore, we have lots of programming languages, so therefore, it's hard to determine which among them will be used for your algorithm. Okay, and also, if you're going to use one programming language for your algorithm, you could not implement it into another programming language. Okay, so there should be somehow, some way that it will be, this algorithm could be implemented in different platform. Okay, so it could use a pseudocode for that, which is the general way of representing our algorithm in the different platform. Okay. So these are some of the properties of an algorithm. So it should accept input, give us a result as an output, and should be correct. Okay, the procedure should be correct, and the number of steps should be finite, and the process should be based on a specific time frame, and it could be implemented in a different it could be implemented on different problems or problems of the same kind. Okay. Now, this is an example of an pseudocode for maximum element. So we create a procedure, okay, and then we define the variables, and we define the loop. Okay, it's almost the same as with C++, with Java, etc. But the main thing here is we use the general words for our pseudocode. Okay, so let's discuss sorting algorithm. So ordering the elements of a list is a problem that occurs in many contexts. For example, to produce a telephone directory, it is necessary to alphabetize the names of subscribers. Similarly, producing a directory of songs available for downloading or for karaoke. So we need to require that their titles be put in alphabetical order. Putting addresses in order in an email mailing list can determine whether there are duplicated addresses. Creating a useful directory requires the word be put in alphabetical order. Similarly, generating a part list requires that we order the according to the increased part number. Okay, so that's some of the examples of implementation of sorting algorithm. So let's start discussing bubble sort. Bubble sort is one of the simplest sorting algorithms, but not one of the most efficient. So it puts a list into increasing order by successively comparing adjacent element, interchanging them if they are in the wrong order. To carry out the bubble sort, we perform the basic operation, that is interchanging a larger element with a smaller one following it, starting at the beginning of the list for a full pass. We iterate this procedure until the sort is complete. Okay, so for example, so the step of the bubble sort in this example, so we begin by comparing the first two elements, 3 and 2. Because 3 is greater than 2, interchange 3 and 2, producing the list 2, 3, 4, 1, 5. Then, because 3 is greater than 4, continue by comparing 4 and 1. Because 4 greater than 1, interchange 1 and 4, producing the list 2, 3, 1, 4, 5. Then, because 4 and 4 is less than 5, the first pass is complete. The first pass guaranteed the largest element is 5. So it is already in the correct position. The second pass begins by comparing 2 to 3. Because these are in order, so we proceed to the next comparison. 3 and 1 are compared since 3 is greater than 1. So therefore, we're going to have a new order, which is 2, 1, 3, 4, 5. And then compare 3 and 4 since 3 is less than 4. So no change. So proceed to the next comparison. 4 less than 5, it's already less than. So next, so we proceed to the next pass. And then, so on the next pass, we're going to compare 2 and 1. So since 2 is greater than 1, so we're going to change it, interchange it rather. So now we have 1, 2, 3, 4, 5, and then compare to 3. So since 2 is less than, so we proceed to the next comparison, 3, 4. Since 3 is less than 4, so proceed with the next 4 and 5. Okay, so in the fourth pass, so we're going to compare again. 1, 2, no change. 2, 3, no change. 3, 4, no change. 4, 5, no change. So the bubble sort will stop if there's no change with the order. Okay, so that's bubble sort. Another example is insertion sort. The insertion sort is a simple sorting algorithm, but it is usually not the most efficient like the bubble sort. To sort a list with n element, the insertion sort begins with the second element. The insertion sort compares the second element with the first element and insert it before the first element if it does not exceed the first element, and after the first element if it succeeds the first element. At this point, the first two elements are in correct order. The third element is then compared with the first element. If it's larger than the first element, it is compared with the second element. It is inserted in the correct position among the first three elements. So for example, the insertion sort first compared 2 and 3. Because 3 greater than 2, it placed 2 in the first position, producing the list 2, 3, 4, 1, 5. At this point, 2 and 3 are in the correct order. Next, it inserts the third element 4 into the already sorted part of the list by making the comparison 4 greater than 2, 4 greater than 3. Because 4 greater than 3, 4 remains in the third position. At this point, the list is 2, 3, 4, 1, 5 pa rin. And we know that ordering the first three elements is already correct. Next, we find the correct place for the fourth element, which is 1. Among the already sorted 2, 3, 4. Okay, so because 1 is less than 2, we're going to insert 1 before 2. So now we have the list 1, 2, 3, 4, 5. Okay, so finally we insert 5 in the correct position by successively comparing it to 2, 1, 2, 3, 4. Because 5 is greater than 4, so it will stay on its position. And that's the last step for insertion. Okay, so that's the end of the video lecture for this session. So second part will be discussed on the next video lecture. Thank you.